If there are questions, we can take more questions. I have time. But what we will do now is spend a few minutes that we have to get an overall idea of what have we done in these 6 hours and why did we do that. You remember the four modules in which I have classified this course. The first was concepts and definitions. The next one, we will look at laws. The next, we will look at properties. And then we put everything together on problem solving. So what we are doing is essentially developing a procedure on how should I solve a problem. And these are exactly the steps that we have to follow in solving a problem. And that's where this thing came up first. That first make a sketch, define what is the system, what are mass inflows and outflows, what is heat, what is work. That was the first thing we do. And then we said, is there a process? Is there a cycle? All of that. So in solving any problem, whether you are asking a question about a fuel cell or whether it is about a power stroke of a diesel engine or a gas turbine or whatever, this is the way to start. So that is the reason why we took it up first. The other reason why we had to do it is that unless we have defined things like the system, like equilibrium, like properties, we cannot fully understand the laws. The moment we take the zeroth law, first law, second law, immediately we will use the words system, boundary, surroundings, properties, equilibrium, all of that will come automatically. The definitions that come out here have to come from here. So if you have to understand the laws, this was a necessity. And that's the other reason why we did this and not the other way around. So let's start with the laws. We need to get something very clear. Only then we can talk of applying the law. Remember, laws can only be applied to a system and to nothing else. Now we know why definition of the system is so important, and the assignment and the problems you will see that if we do not define the system correctly, we could land up in big problems. Having done that, what we have done is that this part of the knowledge is independent of what the substance is. So there's no compromise on this. You cannot say that I will apply this for water, but can I apply it for air? Can I apply it for butane? Can I apply it for aluminum oxide? It's a universal truth in that sense. And so I did not even talk about working substance and the properties of that. That's one thing. The second is the laws will add us some more properties which we have not yet defined, and that and all the other properties will get defined and calculated in this section. So we need to understand the laws in order to decide what are the properties of that substance. And so this leads to this leads to this, and both lead to this, and then all of them lead to solving the problem. And that's what we will do. Even it is a very simple example like some of the problems that I have given. Let's say there is a pipe in which water is flowing, and outside this we have hot gases moving around. And we want to ask the question that if I know something about these gases, how can I predict the temperature rise of this water? From school days, you probably even have the answer that, okay, if this is this, then rho mCp delta T, and you get the answer. We are not going to do things that way because that doesn't help us solve many of the complex problems that we are going to be looking at. We first go from the first step by defining the system boundary. We do all the things that we have talked about so far. Then we say, now for the system, I will apply the laws and then simplify the laws. And then say, no, what is the substance that I have? Then we'll go and get their properties. And then finally, we'll put everything in that formula and we get the answer. So that's why we are going in this sequence. We have now completed this. Now we will go on, and in the next module, which is 29th, 30th, 31st August, we will discuss the laws and their implications. Again, I'm repeating, both of these are independent of the application, are independent of the substance, and we should never have a doubt whether this is applicable in this situation or not applicable. It is always applicable. How can we understand where to choose CV method and where to choose CM method? Okay, The question is, we have two options of analyzing, CV or CM. How do we decide which to choose? What we have done is, we define the system and then we say, is there a mass transfer or a mass flow across the system boundary? If the answer is yes, that means you have an open system. If the answer is no, we have a closed system. And remember, mass means bulk mass, not electrons or protons or photons. Those are not included. If it is open system, we would prefer and we will fix the volume and allow mass to go in and go out. So your volume is fixed, the system is fixed now as a volume, a closed hypothetical space, and we will then apply equations on this. If it is closed, we will apply the control mass approach, even if the system changes its shape and size. Here, the system will not change its shape and size. Okay? So that is the conditions under which we decide whether to apply CV or to apply the CN formulation. What is the difference between heat transfer and thermodynamics? Okay. These are two different subjects. The subject of heat transfer, whether it is mechanical engineers, chemical engineers, and many civil applications, aeronautical applications, it deals with how heat transfer takes place in a solid, liquid, or a gas. Basically, the transport of energy. So the shape, the size, the properties, the temperature gradients, the flows, that is what is looked at here. Whereas thermodynamics is essentially looking at the interconvertibility and the relationship between heat and work. So that's the science is different. Here heat is something that went from surrounding to system or system to surroundings. Here we say, look, I have a rod and there is heat transfer taking place, or I have something which is hot over which air is being blown. What is the rate at which it cools? That question is not answerable by the knowledge of thermodynamics, but that answer comes from knowledge of heat transfer. And at least in liquid and gases cases, you also need to have a knowledge of fluid dynamics. So it is the governing laws of physics here are Fourier's law of conduction and the radiation laws. Neither of these come into a course on thermodynamics, and the interconvertibility of heat to work is not talked about in heat transfer. Okay, so that's the difference. And yes, all the applications we have seen, fuel cells, power plants, aircraft engines, human body, everything, there is a thermodynamic aspect to it, but really making it happen, designing of the components, we go to the heat transfer part and then do all the calculations from there. So the two go one after the other. Okay, next question. Okay, what is a dead state in thermodynamics? I don't think we use this term here. Then there's another question that says electricity has better quality than heat. Then why it is not used in automobile system? Okay, you will find the terms in several books and articles on what do they call a low grade heat, low grade energy, high grade energy. These terms are, you will come across these. We haven't defined it here. We'll wait till the second law comes in, and then we will see what do we mean by saying that what is low grade and what is high grade. At that point, we will look at these discussions. So we need to come back to that point. But why electricity is not used in an automobile? The reasons are fairly straightforward. Your problem is how do you generate it? And yes, you can Okay, that question is there. Why don't we use electricity in automobile? So to see why we don't use it, let's see an application where we do use it. And the application where we do use electricity is the railway locomotive. The diesel locomotive that you see on the railways, not the electric locomotive. What it does is that on the locomotive, it has a diesel engine. This is coupled to a generator. This goes through controls, and then this powers electric motors that drive the wheel. So this power goes there, and this is the wheel on the rail, which then is driven by a motor and a gear system. So that is what is a diesel locomotive. And strictly, it is not diesel, but diesel electric locomotive. So there are many engineering issues that were there, why it became a diesel electric locomotive and why don't we have a conventional clutch and a gearbox in a loco. It just broke many times. So finally said, it is impossible. Yes, I can make it, but in a few days it will break. So don't market it. But this has become the stable design, and almost all diesel locomotives are actually diesel electric locomotives. And here controlling is much more easier. And it is also possible to do one more thing, is that when you want to brake, you'll have to dissipate the kinetic energy, but at certain speeds, the kinetic energy of the train is converted into electricity by the motor, which can be made to operate like a generator, and that heat is dissipated through heaters as I square R loss. But talking of the electric vehicle though, if you look at yet another version of the railways and look at the electric train or the electric locomotive, this is getting power supply from overhead cables. So it doesn't have a combustion engine or a fuel cell or anything inside it. And what people are increasingly doing now is that when the driver is applying the brakes, the kinetic energy of the loco and the whole train is converted into electricity by the motors operating as generators and fed back to the line that some other locomotive or some other user can use it. This is a great advantage, and this is called regenerative braking. And right now we can recover a certain amount of energy of the train into this. There's a lot of work going on to see how we can convert more of the kinetic energy of the train and make it back into electricity which somebody else can use, so then you don't burn that much fuel in the power plant. So in that sense, this type of a technology is possibly the most efficient technology you can think of. And that's why if you see energy consumed for moving one person in a metro train or an electric train, it is much, much less than either a diesel bus, which in turn is much less energy intensive than the car. Regenerative braking in a car or a bus is very difficult because in a very short time, you got to convert a lot of kinetic energy into electrical energy. And then batteries do not have the capability to store that fast. The recharging of batteries takes time, and so regenerative braking in the context of an electric vehicle has a very limited use. But theoretically, yes, doable. Yeah, there's a question. Yeah, please go on.
Sir, how can we check whether a process is thermodynamically feasible or not?
Okay, so the question is, how can we check whether a thermodynamic process is feasible or not? Okay, the actual answers will come when you look at the next module, but very quickly the answer is this. Any process that violates the conservation of mass is not feasible. So you say that I have something into which in a steady state I have 5 kg of water going in but only 3 kg of water coming out. That's not possible. So if it does not violate the conservation of mass but violates conservation of energy, not possible. If it obeys conservation of mass, is okay with conservation of energy, but violates the second law, not possible. So if any of these happens, we can conclude that that particular process is not possible. Okay. So whether it is designing a turbine, whether designing a nozzle, a rocket, or designing something for heat transfer, these things, any of these things get violated, that process is not possible. And in the next module, we will start putting criteria by which you can say, how can I calculate and say whether this process is possible or not possible. Okay, even though solar energy and IC engines were known to us a century ago and their efficiencies were too low in the beginning, then why IC engines developed faster than solar? Okay, so the question is, why IC engines have developed faster than solar? Okay, the answer is very simple. IC engine development and the use of the automobile has only one criteria: the price of oil, that is how many dollars per barrel. Okay, as there was a time in the 70s, oil was $4 a barrel. Then after the oil shock in 73, it went up to like $20 a barrel. Then it went up and down and got back and remained low again for a very long time. Then in between it shot up to $150 a barrel. And then again it came down and hit again like $15, $20 a barrel. So as long as there is cheap oil, we are not going to go for renewables at all. What happened was, when oil hit $150 a barrel, people suddenly started looking at solar energy and renewable energy in a very serious way. Again, when the price of oil went down, or before it, when the price of oil went rock bottom, you saw people driving SUVs and big cars, and nobody bothered about the fuel efficiency of a car. So to say whether IC engine developed faster or not is a debatable question. But the fact was that the average fuel efficiency of cars in periods of low oil prices has been worse. It has not increased a lot. Second, the IC engine in a car hasn't really developed that much. If you say that, how do I compare it with solar? Well, if you look at the efficiency of the solar photovoltaic cells, or the way we are able to now run, say, a thermodynamic cycle using solar, or the fact that we did have a power plant that runs 24 hours and generates electricity, that's a big advantage. That's a big achievement. So to say that there were no achievements in solar is not right. The fact is that the IC engine hasn't had that many great achievements to show for itself. And even if all those things would have happened and you make a car which has got 100 kilometers per liter and throws out nothing as a pollution, and everybody has that car, ultimately you have to live with the reality that on the road the space is limited and you will again be spending all your time driving through traffic jams. That doesn't get us anywhere as a society. Okay. What is the difference between point function and path function? A point function, we say that if the properties of the system do not depend on its history, then it is a point function. But if it depends on the path by which it got there, then that is a path function. That means here it went through a series of states, and if I do some mathematical operation on these, and this depends on the path taken, then this is a path function. But if we come from here to here, whether by this path or anything else, and it doesn't care how it happened, then this is a point function. So all our properties, these are point functions because it doesn't care how you got there as long as the system is there. But heat and work are two, they depend on what path you took, and over that entire path, it depends what happened during every little point on that path, and then we did a mathematical operation to calculate Q and W from that. So they are path functions. In this case, end states, the initial and final states are not just enough. Okay, that you can take it there. Okay, so so we will. That brings us to the end of this 6-hour module. I have given some practice questions. Please try those. If you have difficulty, discuss amongst yourself and do the best you can. You will also get the solution. I have given that. Learn from it. If you make a mistake, that's okay. but learning from the mistake is more important. So learn from it, and if you still have doubts, we can again meet later on and I can take on your questions. After that, I have given a practice quiz so you can check how well you have understood the subject yourself. If you have again make any mistakes, please go back and relearn and figure out why that happened, because these are concepts which will keep coming back again and again in the remaining part of the course. And finally, I have posted a proctored quiz, so that is the quiz on the basis of which you get some marks. Okay, so thank you.